Welcome back. Chemistry, at it again. A few days ago I had 0 subscribers on my channel. Today, as of this moment, I have 17, an increase of infinity%. So at that rate, I will catch Anna in no time. And I mean literally no time. If you're increasing at infinity%, you will get anywhere you want to get in 0 time, literally. A small infinity reference for people that understand infinity. We have our first question of the year coming from our viewing audience, which is, what do you do if the temperatures in the homework are wanted to be in Celsius? So the answer is, at the beginning you make everything Kelvin. At the beginning you work all the equations using Kelvin. You would get temporarily what would have been the answer in Kelvin, but then if they request specifically a Celsius answer, then at the end, the last thing before you write your answer down, you'd have to take the Kelvin temperature you already got and subtract 273, and then that would be your Celsius answer. There have to be more questions out there, so please email them and I'll keep answers coming. Today we're in 11.7. So 11.7, the star of the show continues to be that equation continues to rule our life the way it did yesterday. Yesterday we were working 20 to 28 using that over and over. Today we will use this again over and over, but the questions have one small thing to do at the beginning of the problem to change it, which is either going to be a little bit of adding sometimes or a little bit of subtracting sometimes. So we're going to have a very basic math move to do at the beginning to add or subtract, and then this we're going to repeat the scheme. So I'll get to some math here in a minute, but today on the 11.7, new ideas you were trying to find were Dalton's law of partial pressures, and then the second fill in the blank was sum, because as I referenced a second ago, today we're either adding or subtracting when it's time to do a little bit of math, one little step before we go. 3 was from the page where they talked over and over about high altitude and what's going on and what your body does at high altitude to accommodate an oxygen level. It makes more red blood cells, and if you ever wondered why sports teams fuss when they're in those altitude cities, or if you've ever wondered why the Kenyan runners have an advantage, it's because they train in high altitude, because Kenya's high altitude. Different runners for longevity events, they'll train up in the mountains just because it's an oxygen benefit to them in the long term. Your body has to adapt when there's less oxygen at high altitude, and it does that by making more red blood cells and just adapting to accommodate oxygen. But there's a page explanation of that if you really care about the nitty-gritty details, but that's what they were talking about for that page. But your body would make more red blood cells there. When you travel, sometimes you get tired. That can have, varied effects on that, but to a degree, sometimes that can be altitude, depending on where you're traveling and how. Next time when you see a paper, 11.8 is the read. 11.8 is going to have 3 new points of content. There's going to be a new equation, so it'll have a name, it'll have an equation, and there's a number that goes with this. It's like a preset number that I'll use in every problem, like pi is 3.14. It's not pi, but there'll be a number in that reading that it's a number we need to know to do the next bunch of math that's just used in that equation the same way over and over and over again tomorrow. The questions rework only very slightly. Everything today from what is pressure to the bottom just is what it is. None of that's going to change. 1, 2 stays the same fill-ins. 3 stays the same thing about making more red blood cells. And then here's a question that's new that will affect this math problem. They talked in the reading about how sometimes when you collect a gas, you're near a water source and some water vapor just gets mixed in. If you're near a water source, if I collect gas in my room, it's not the same as if I collected gas down by the river if I were fishing, which I don't really fish, but if I did and I collected gas down by the river, I'd get some water vapor mixed in and it would muck up the measurements. So the question is, if you have a wet gas pressure, how you find dry gas pressure? And the answer for now, which may not make sense until we actually do it, is to subtract the water vapor pressure. So subtract water vapor pressure is a phrase I'll come back to when I'm looking at this. But in the homework, if it says collected near water, or if it says something about a wet gas, that means there's some sort of mix of water vapor in there that we don't want counted when we do our normal mathy stuff. So I told you we were going to have to either add or subtract in these homework problems to start. The Dalton's law of partial pressures is going to be an add. The other wet gas thing would be a subtract. So I'm going to see who's calling into our show. This is our first live phone call during our show, but we're going to talk recorded. And we're back. Special Evangel Heights greetings from Anthony and Fonte out there to any his former Evangel acquaintances. I was him on the phone trying to talk some sports planning. I believe where we left off was the idea that if you have a wet gas pressure, you have to subtract the water vapor pressure, which you'll understand better when we actually do that. So where I'm headed now is to page 291. So if you want to join me on 291, this would be an example of Dalton's law of partial pressures, which means we're about to add some things. So it says a 1 liter cylinder is at 27 degrees, contains a mixture of 3 gases. There's a gas A that's 300 torr, there's a gas B that's 250 torr, there's a gas C that's 425 torr, and they say calculate the total pressure in torr of the mixture. This is going to be your favorite math thing we've done in a long time, because to figure out the total of those pressures, you're just going to have to add them all. So we just do that, plus that, and you're looking at 975 torr, part A, that's it. Total pressure, just add up all the partial pressures. Each of these is a partial pressure, add them all up, you've got a total pressure. You hope for a lot of those, but I don't think there's a lot of those, but that's a good news problem. For B, they're going to then want us to go to our equation that rules the world. And just do what we did yesterday, do what we've been doing for a few days. So what they want us to do for part B is figure out a volume in liters at STP if gas A is removed. So we need to backtrack a minute. Gas A is removed. So this is not our total anymore. They changed the game slightly. It's only these two. So if we add up these two, that's 675. Or if you prefer, sitting from the 975, when I cross this out, subtract 300 off, all roads should lead you to 675 torr. And then we just plot these things as we have been each time. So they're saying to us, at the beginning, we have 675 torr, and that is a pressure. Pressures always go here. The pressure is any of those 8 units from the quiz, the ATMs, the torr, the pascals, the millibars, all that stuff. So 675 torr is our starter pressure. 1 liter was our starter volume. Volumes are always milliliters or liters. The original temperature is 27, so we need 27 plus 273 is 300. And if you haven't noticed yet, that is their favorite temperature they like to use. They like to use 27 because it adds 273 to be a nice round number. You've probably written 370 times, I can't imagine. In the new creation, they want us to get to STP and find a volume in liters. Since this was in liters, this can be in liters. That's good news, no mismatched weird stuff. 300 gets replaced by 273 because that's just a memory number. That's the standard temperature number in Kelvin. 675 was torr. We memorized the standard number of torr, which is 760. And now we're basically doing what we were doing yesterday. The only difference compared to yesterday was you had to add these up to come up with the 675. But other than that, it's the exact same thing. So X is on top, that's our desire. Again, if the X is ever on the bottom, we talked in yesterday's video how to zigzag those numbers. You could go back and rewatch that if you needed to do that. One suggestion that's probably the simplest to understand is just take both fractions and flip them both completely upside down. Anything that's with the X has got to go oppositely. Since this is on the top, we're going to travel that to the bottom. Since this is on the bottom, travel it to the top. every number on the top, hit the multiply button, every number on the bottom, hit the divide button. So 675 times a 1, if you wish, times a 273, divide by a 300, divide by a 760, punch, 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 peeking at my answer paper. Your screen should read you a 0.8, a 0, and then in the third position, a number that will round to 8. This was a volume slot. Matching this volume slot was liters, so we are liters, and then that one is good. For 11.9, we need to go up a page. 11.9 is on, actually up a couple pages, to 294. 294 says volume of a certain gas collected over water. Collected over water is a magic phrase that means you have a wet gas. They also might say specifically wet gas, but if it says collected over water, same thing. When you hit these, you have to go back to the phrase that I said a minute ago that I said it wouldn't make sense until now, and now hopefully it will. What we have to do is subtract the water vapor pressure. Wet gases cannot do the equation and work. Only dry gases can do the equation and work. So when they give you a wet gas collected over water, before we can use this, we have to subtract the water vapor pressure. And I'll talk about that in a moment. So I have my 720 written down. I'm going to have to subtract off a water vapor pressure that I'm going to have to locate in a table. So let's do that while we're on topic. I think in the packet I sent home a table, but I was not wise enough to keep a spare packet for myself. If I ever do an experience like this again, I think I'll make a spare packet and keep it myself to know exactly what I put in there. But I think I put a table in your packet. If I did not, the table was copied from page 616 in the back. There's a page 616 that says Appendix 5, water, vapor pressure of water at various temperatures. I'm pretty sure I copied that on a half sheet and put it in the packet, but if I didn't, sorry, you're going to have to bookmark that page or take a picture of that page or do something with that page and get back and forth, because this is how we're going to come up with our subtraction number. So back to 294. 294, it was talking about 30 degrees Celsius. So I need to take the knowledge of 30 degrees Celsius to that table. And the table is going to read down, down, down till I find 30 degrees Celsius right about here. And then I'm going to trace across and grab one of these numbers depending on which unit we're using. So since we were doing torr, the 720 is torr. I need to get the torr number from this column. So 30 links to 31.8. And so I'm going to use the 30 that they gave me for the temperature. Whatever temperature they give you leads you to a number. 30 degrees from the story leads us to 31.8 in the torr column, and then we're done with that table. No one in the world is memorizing that table. The table would always be a thing on a test or homework or whatever. You'd always be given a copy of the table. If you're on a table, that table for this chapter, you would just have it. But for this, we are subtracting 31.8, and then it is 688.2 torr is the dry pressure. This 688.2 is going to go in the equation. 720 cannot. Okay, so that's again our modifications before we do the stories today. If it's a partial pressure story, you're going to have to take the partial pressures and add them. Get a new number, that's going in the equation. If you have one of these wet gases, you're going to have to use the table in the back of the book or on the half sheet if I did remember to copy that for you. And we're going to subtract the magic number we get from our table to get a new pressure. And now we're going to do the same thing that we've been doing. There are no bonus features on this video today. Sorry, hope you enjoyed yesterday's bonus features. But if you understand how this is going to work, you might as well just stop the video because you've now done this a lot of times. But if you're hazy at all on how to do this equation, just keep listening, but there's no new or funny things going to happen, I don't think. So working this equation, 688 is the original amount of torr when we collected it. That is a pressure, so 688.2 goes there. We have 150 milliliters in that sentence originally. 150 milliliters is volume, liters, milliliters, always volume. 30 Celsius, 30 can't live here, Celsius cannot be ever used in a problem. 30 has to add 273 to make 303. And then we're trying to get 2 milliliters, that's good news. This was milliliters, so this is milliliters, no need to change anything there, they stayed consistent. If they had made one of these be liters, we'd have had to do a change. If they're doing that and it's confusing you ever, email me and I'll do a quick conversion seminar on that. So they're talking about STP. So 688 torr is going to have to become 760. 760 is our memory number again, just like it was over there. 273 is our standard temperature number, just like it also was over there. The only number from the story we didn't use is the 720, but we sort of did. 720, again, couldn't go in the problem because it was a wet gas. 720 had to subtract to make a new number to do the equation. Again, variables on the top, it usually is. Odds are heavily in favor of that. And now we've got to just do a little cross multiplying. 760 is down, 273 is up. So 688.2 times 150 times 273. Divide by button for 303, divide by button for 760. You should only have to hit enter once. Punch that in one big thing that fills your screen. Hit enter. Paper over here says that your screen should read 17 and then something, nope, that's a lie, 1, 2, and then something that'll round to be another 2. And since this was milliliters, this is coming back to us in milliliters. Very brief seminar, that's done, okay? But if they had demanded from you liters, you'd have to go like this. Milliliters go away, liters come in, and then 1 liter is the same as 1,000 milliliters. So this would have to divide that to tweak it into liters. They didn't ask that there, but if they ever ask that again, go ahead and that's what you would do. And that's it. See you later, chemistry.